Hi, my name is Daria, and today I would like to talk about the importance of the tracer for extracting filaments. Thanks for all previous speakers to talk about my introduction. But as you know, we have many surveys which show that galaxies in the universe are not distributed uniformly. And we see the structure, which we call cosmic web, and the probably most incredible thing that properties of galaxies depends on where they appear. So galaxies in denser environments, such as clusters, they are redder, more massive, have lower star formation rate, and so on. And we also know that today we also know that galaxies also in filaments and walls have different properties from the galaxies of in clusters and galaxies in the voids. But to investigate it more detailed, we need to know how identify the different environments for the galaxies. And first of all, we need some tool to identification of environments. And today we have a lot of possibilities. Here are some examples, and you can select on how you prefer. It depends on the ideas on which these tools built, from topological methods up to deep learning. It exists, but in real universe, actually, we do not able to investigate distribution of dark matter. We can use only distribution of galaxies, which are biased indicator of distribution of the whole matter in the universe. And it was a main topic of our work. We stressed how the galaxy bias, which depends on the epoch where we consider, and on the properties of the galaxies, such as mass or luminosity, depends, and how this galaxy bias affects our identification of filamentary structure in the universe. And to do this, we use semi-analytical galaxy evolution model, Galaxy Evolution and Assembly, which coupled with Millennium simulation. And to identify filamentary structure, we use disperse as the most common tool for identification filamentary structure. We select 27 cubes at Z0, and 9 of these cubes has in the center of the cube Virgo similar halo by mass, 9 of them comma similar halo in the center of the cube. We do it since Virgo and comma is close to us in most investigated halos, clusters, so we can compare with real data how it's going. And also we select 9 randomly cubes to mimic general fields to see if there exist differences between Virgo, comma, and randomly selected cubes. And here's an example for one cube. On the first panel, you can see distribution of galaxies, massive 10 to 9 solar masses, and filament system which extract only using by these galaxies. In the center panel, distribution of dark matter for these galaxies, and the corresponding filament system by blue. We call it dark matter filament system. And in the third panel, you can see on one plot the galaxy filament system and dark matter filament system, and they do not coincide totally. So we see some differences between galaxy filament system and dark matter filament system. We tried to measure it to compare somehow between cubes and how we can improve our coincidence of the filament system. We use several metrics, but I would like to discuss on the simplest one. It's we measure distance between two skeletons, between a red one and the blue one. Just we're trying to find the closest part of the filaments for another skeleton. For example, if we select part of blue skeleton and try to find the nearest red one. And here is the distribution, probability distribution function for reference dark matter filaments. We trying to find nearest galaxy filament system. And we see this, each line represents one cube, and we see that this distribution shows bimodality, and it's definitely means that first mode, it's show the fraction of the dark matter filaments which coupled with galaxy filaments. And the second mode is show that dark matter filaments which cannot be detected by distribution of galaxies massive 10 to 9. And now we can express it in percent. So we found that only around 60% of dark matter filaments can be detected by distribution of galaxies massive 10 to 9. And we also trying to understand exists some dependency on how massive cluster in the cube exists. Since Coma and Virgo is pretty massive halos, but we do not see improvement of coincidence for dark matter and galaxy filament system. Depends on how massive halo in the cube exists. So around 40% of our dark matter filaments do not contain enough galaxies massive 10 to 9 to be detected, but probably so this 40% of the dark matter filaments have enough dark matter to be detected by distribution of dark matter, but do not have enough galaxies. Probably in these filaments wasn't enough gas to form these galaxies, such mass. Probably they contain enough galaxies of lower mass. We're trying to test it, and here you can see the previous one plot where red filament system was identified by galaxies massive 10 to 9, and the pink one is a filament system extracted by galaxies, but massive 10 to 7. And as you can see, the highlighted in previous slide area, even in this case, do not show coincidence with the pink one filament system. And also you can note that pink one do not coincide with red one. To explain this, I would like to show the slides around the coma-like halo. Here you can see distribution of dark matter and corresponding filament system, and distribution of galaxies massive 10 to 9, 10 to 10, 10 to 9, 10 to 8, 10 to 7, and corresponding filament system. And distribution of the galaxies massive 10 to 10 tends to appear near the dark matter filaments system. And it's not a really new result, because it was mentioned in many other work that massive galaxies tend to be found in denser environment. So the massive galaxies show that in this area there are a lot of dark matter to form the massive galaxies. But when we consider lower mass galaxies, we see that galaxies massive 10 to 9 also appears somewhere near the denser environments, but low mass galaxies such as 10 to 7 appear everywhere, and they create a mess and create a noise. So that's why we cannot improve our detection of the filaments by galaxies of lower mass. And to support this, we measure distance of the distance from the galaxies of certain mass to dark matter filament system as the reference, and you can see that the most massive galaxies, massive 10 to 12, tend to be found more than 70% of them near the dark matter filament system. They are pretty close to filament axis. And in contrary, low mass galaxies, galaxies between 10 to 7 and 10 to 8, only 22% can be found near the filament system. So they are the most probability to find low mass galaxies quite far from the filaments. And the second parameter to compare filament system is connectivity. It's a number of unique connectivity of the halo. It's number of unique filaments which goes to the halo. From one side, it shows the branch of the system from geometrical point of view. From physical point of view, it shows number of flows which gain mass to the halo. And as you can see, for coma-like and Virgo-like halos, dark matter filaments and Galaxies filaments show the different behavior. And we can count number of connect filaments to each halo in our 27 cubes, and it depends on the mass of the halo, number of filaments which goes to the massive halo. And this result was also showed in many other works, that connectivity of the halo depends on their mass. But also we found that for Virgo and coma-like halos, by mass, the number of dark matter filaments is higher than number of galaxy filaments. So we have some underestimation of the filaments of the filaments which goes to the cluster if we're using galaxies massive 10 to 9. And can this parameter will be improved? Can be this parameter improved by considering lower mass galaxies? Because as you can see in the same picture, the number of the massive galaxies actually is quite low, and it cannot help us to track all connectivity. But for low mass galaxies, connectivity in this example shows pretty the same results as for dark matter filament system. And on the plot, it will be it will be such this. And you can see the yellow line, it's for galaxy filament system for galaxies massive 10 to 7, and let's try to reach dark matter filament system. So low mass galaxies can improve our understanding how many filaments flow to the massive clusters. And this is a summary that galaxies with mass 10 to 9 can trace around 60% of dark matter filaments, and independently of the galaxy's mass. But when I say 60%, it really depends on our detailing of the filament system, because we are always free how we would like to see detailing of the filament system. Here is one example. It's slides, and you can see two filaments. Red one represents galaxy filament system, and blue one dark matter filament system, which do not coupled. And we can increase detailing of the filament system, and new filaments appears, and the upper filaments now coupled by red one, and we can go further and decrease or increase higher our detailing filaments, and appear more filaments. But and it's improve our coincidence of the filament system, but still we can found the filaments which do not show coincidence. So galaxy bias influence on our identification of the filament system, and this result in our work was the same result was mentioned in the legal work in 2018. They use Cosmos survey to identify filaments using photometrical information about galaxies and spectroscopical information of galaxies, and they built two filament system, and also they use horizon AGN simulation to build for this corresponding distribution of the galaxies, dark matter distribution to extract its green lines, and they do not coincide between red lines do not coincide with black one, and green one do not coincide with them all. So we see that extraction of the filaments can be affected by properties of the galaxies. And properties of the galaxies play a role in the identification filaments. And mass probably the most of the role, because low mass galaxies can improve connectivity detection, but for large scale identification they create a noise for extraction, since they can appear in the filaments and the clusters and in the void. And contrary, massive galaxies, they can improve they cannot improve also our coincidence, but they are tracer of dense regions, but they are little number and they cannot highlight connectivity for our purposes. So that's all.
Dmitry?
So disperse have such parameter which is persistence, right?
Yes.
What choices did you make, and did you try to investigate separately high persistence features from kind of low persistence?
Yeah, we play with the persistence, and so here I showed it's literally we changed persistence to increase detailing of the filament system. Yes, of course, if you have the cube with volume and you increase the detailing of the filament system, they will coincide better, but it's just because you put inside the cube bigger number of the filament, they should coincide in this way.
Yes, but more question is to go element by element and judge its own persistence compared only high persistence features from both.
Yes, we tried, but we try to focus on the fixed persistence to compare it.
So you check the filament recovery for different galaxy masses, but I would say that even for the dark matter, there is a choice in, I suspect that for different resolutions, or you would get different filaments also within your dark matter field. So can you comment on that?
Yes, it should be, but we also have a galaxy bias, and it will affect our results in any way, even if we have a best resolution for dark matter or real data for dark matter. We also have a galaxy bias, and it will affect our extraction of the filaments.
And so, but in this case, you did not apply any smoothing to your dark matter for.
No.
And so it's applied directly to the dark matter particles.
Yes, we use whole Millennium simulation.
Yes. Just a clarification, the 60%, does that refer to the galaxies in filaments that are traced by galaxies, or does that refer to the filaments?
Dark matter filaments.
No, but I mean, so you said you miss galaxies, or is this a comment on the number of galaxies, or is this a comment on the number of filaments that are traced by galaxies?
Number of filaments.
Okay, do you know the other one, the number of the galaxies?
Galaxies filaments. No, galaxies which are
Inside
defined as, yes, it's around 80% of the galaxies will be defined as member of the filaments in both filament system. Yeah.
Yeah, just apologies if I'm asking the same question that's already been asked, but this 60%, is this already a maximum based on varying things? Because if it's not, it would be useful to use this to figure out how best to find filaments in galaxies that trace dark matter by figuring out by searching over all the ways of finding filaments to get that number bigger than 60%.
Yeah, this number really depends on what we consider as the filaments. Would we like say that it's filament by dark matter or by galaxies? And if we say this is filaments, this number can change, but we still have a galaxy bias. And that's the main point, that we can't recover probably fully dark matter filament system only using by galaxy.
Sure, no, I understand that. It's just your work might be useful in a way that you might not have thought about by informing people working on Euclid or whatever.
Yes.
How to find galaxy filaments in order to best
paper.
trace them. So that would actually be quite interesting to study, I think. Thanks.
Any other question? Yes.
Thank you. So between the two methods, did you compare like filament properties? Like, does one method give you longer filaments and another give you shorter filaments?
Which method? Sorry.
So between the dark matter filaments method and the galaxy filament method.
You mean this one?
Right. So I'm asking, so, you're comparing like the filaments, but did you compare like properties of the filaments? Like, did you compare like, does the dark matter filament method give you like longer filaments?
Yes.
Okay.
Yes, dark matter filaments longer, but it's, for my opinion, it really depends on number of samples in the cube. For dark matter particles, we have around 40 million particles, and for galaxies around 20,000, and it's dispersed is really sensitive to number of sampling. So we obtain the quite longer dark matter filaments, but I think it's artifact of disperse.
Thank you.
Any other question? Chris?
I guess there's a question of, did you compute the distance both ways, from the dark matter to the galaxies and from the galaxies to the dark matter?
Yes, we measured it the same.
Because when we wrote disperse, we looked at the, forgetting about galaxies, if you just give yourself a dark matter simulation and you change the persistence, say you use 3 and then 4 and 5, what you would build is a skeleton which grows like a tree. So yes. The low persistence would, the very high persistence would be like the trunk, yes. And then you would add the branches and then the leaves, etc. Yes. So if you measure the distance from one skeleton to the other, one distance will always be 0 because you always get, if you get both the trunk, the branches and the tree, yes. Then the distance to the trunk is 0. Whereas if you do it the other way around, you would get a different answer.
Yes, but It's the same order. Around 60% of the galaxy filaments do not have. But in our selected detailing of the filament system, we can change the persistence level, and this number will be changed. It depends on the scale which we would like to consider.
Any other question? Okay, let me ask final questions. So in my opinion, so your results basically reflect the existence of nonlinear anisotropic bias combined with assembly bias, because there are several actually popular models for these biases. So I think it might be possible to predict this 60% difference between dark matter filaments. So do you have any comment on it?
This number is really attractive to say that only 60% we can, but it really depends on our detailing of the filament system and our definition, what we consider the filament.
But still using those anisotropic nonlinear bias factor, and it has been calculated from numerical simulation.
It should be, but we did not do it.
Okay. Okay, thank you. Okay, let's thank all the speakers of this afternoon session.